Hi everybody, this is an adjunct lecture to lecture 21, so I'm going to call this one 21A, and 21A is the completely worked out problem 449. Now in your textbook you can draw heavily from a sample problem, which is sample problem 4.4 on pages 266 and 267. So what I've done here is I've worked out problem 449 using this sample as using sample 4.4 as a step-by-step example. In this short video, I also point out some pitfalls and make some corrections and additions to what was done in lecture 21. So to get started, what we basically have is a block of concrete that is 300 millimeters wide, 540 millimeters tall, and in the bottom we have embedded 4 steel rods. The centers of the steel rods are 60 millimeters from the bottom. When we apply a positive bending moment of 175 kilonewton meters, the question is, what is the normal stress in the steel? What is the normal stress in the concrete? Well, the normal stress in the steel with a moment configuration this way will be in tension, which is positive, and in the concrete will be negative or in compression. And this is the only configuration that works for reinforced concrete, because the steel is embedded in the concrete in order to make the concrete bear tension, which, as we talked about in class, concrete is very poor in tension, so really everything below the neutral axis of the transformed section of this concrete will not do anything except for hold that rebar in place. So the first step is to draw the geometric diagram, recognizing that we're going to have a transformed diagram that looks different than that, but that represents more how it looks to the stresses, for lack of a better term. So we draw a transformed section. We do not know the location of the neutral axis, so we do know that the top portion is, or that the actual concrete is 300 millimeters or 0.3 meters wide, but we just know that it's x from the top to the neutral axis. We also know that the centroid of the concrete to the neutral axis has that length is x over 2. Now, because the entire height of the concrete is 540 millimeters, but the center of the rebar is 60 millimeters off the bottom, that we just take the height, the effective height of the transformed section is going to be the actual height, 540, minus the distance between the bottom and the centers of the steel. So that gives us 480 millimeters from the top to the center of the steel rebar, or 0.48 meters. Now I've turned everything into meters as well because I just find it's really easy to get into the weeds with using meters and millimeters in the same problem. So I always take things to base units, but that is a personal preference. If you're comfortable working with it a different way, then that's fine. The third thing we do is to calculate the actual area of the rebar, and then we calculate the transformed area of the rebar. So the area of a circle, and each of these pieces of rebar has the cross section of a circle, would be pi d squared over 4. And in this section there are 4 of them. So we multiply this quantity by 4 and we come up with an area of the steel equal to 1.96 times 10 to the negative 3rd meters squared. Now to calculate the transformed area of the steel, we multiply by the ratio n of the modulus of elasticity of the steel to the modulus of elasticity of the concrete. So n is 200 GPa over 25 GPa, which is 8 even. So multiply 8 by the calculated area, and we come up with a value of 1.57 times 10 to the minus 2 meters squared for the area, the transformed area of the steel. The next step then is to solve for the location of the neutral axis, because that will also give us x, the height of the concrete above the neutral axis, or the effective area of concrete. We use the theory of first moment. This is from chapter 5 in your statics book, where the first moment of area about the centroid of any object is equal to 0. So in this case, for sections like this, the neutral axis is located at the centroid. So I take the first moment of area above the neutral axis, which is the area, 0.3 times x, of the concrete block, times y, which is the distance from the centroid of that area to the neutral axis, so it's x over 2. And then below, I have the area of my transformed steel multiplied by the moment arm, or the distance from the transformed section to the neutral axis. And I set those equal to 0 in order to find the location of the neutral axis. All right, so then I just rewrite this to make it look a little bit cleaner, and I develop this equation, which is a quadratic equation, or a second order equation, 0.15x squared plus 1.57 times 10 to the minus 2x minus 0.7536 times 10 to the minus 2 equals 0. Now, I want to point out that when I was working this in class and on the first video, I mistakenly squared this second term, and that is not correct. If you look at the units here, we have a distance, a length times a length times a length. So the units of Q are L to the third. Here, this is an area, which has the dimensions of L squared. So this needs to have the dimensions of L. And if you look at sample problem 4.4, they did not accidentally square this. This was my accident in class. So I want to point that out so you realize that it's just the area times that distance. Okay, so we simplify that, and then we use the quadratic equation to solve for x. We're looking for the roots of this equation. So a is the coefficient of x squared, b is the coefficient of x, and c is the constant term when this is set equal to 0. Quadratic equation says the roots occur at negative b plus or minus the square root of b squared minus 4ac all over 2a. So I plug in those numbers, and I get basically 2 roots. In other words, when I come to this part of the equation, we could have negative 0.0157 minus 0.0691, or negative 0.0157 plus 0.0691. The only root that makes sense is the positive root, because x is the height of the concrete above the neutral axis. So it doesn't make any sense that it could be a negative number. So I only solve for the positive value of x, and I get 0.178 meters equals x. So if I look at my redrawn transformed section, that means that the height of the concrete is 0.178, and the distance from the neutral axis to the transformed rebar is the entire height, which was 0.48, minus 0.178, or 0.302 meters. All right, the next thing we need to do is to calculate the moment of inertia about the neutral axis. Now, unlike first moments of inertia are always positive unless the area itself is negative, which is not going to happen in this particular case. But we have I of the concrete plus I of the transformed steel. The I of the concrete about the neutral axis, if you look in the back of your book, the I of a rectangle about its base is 1/3 base height to the third. And the second part is, because it's a transformed area, we really can't use that, but we can use this most general form, that the I of the steel is the area of the steel times the distance from the steel to the neutral axis squared. So we plug in those numbers, and we come up with a value of I, the moment of inertia of our transformed section, is 1.995 times 10 to the minus third meters to the fourth. Okay, now finally we get to the point where solving is in order. We solve for the sigma in the steel, which is equal to n, that ratio of moduli of elasticity, because we essentially have to transform the steel back, times the moment, times the distance from the neutral axis to the centers, or to the transformed steel, divided by the moment of inertia. So I go through the work, and I come out with this units in kilonewton per meter squared, which would be kPa, and I divide by 1,000 to get MPa. Now, the sigma in the steel will be in tension. Otherwise, there's no point in having it there. Now, to find sigma max in the concrete, we talked about the fact that this is a linear relationship where it starts as a maximum number at the very top, and then a maximum absolute value, and it proceeds downward in a linear fashion at least in a homogeneous section. So we just take the moment, 175, times c, which is the distance from the neutral axis to the top, or the height of that concrete block, and divide it by I. I know from my work up here that that unit will come out to be kPa. So I do the solution, and it's 15,614 kPa, which is 15.6 MPa. Now this is the concrete. The moment is positive, so this is in compression. You can indicate that either by saying 15.6 MPa in compression or by saying negative 15.6 MPa. It's not really correct to say it's negative 15.6 MPa in compression, so you choose one or the other. All right, and that is the correct answer, and that's the solution to problem 449. So on Monday we'll have a review for our midterm exam, and then we'll proceed forward from that point. Have a great weekend.